Welcome to my presentation on the road towards safe and energy efficient automated driving. My name is Stephen Peters and I am professor at the Technical University of Darmstadt and heading the Institute of Automotive Engineering in Germany called FZD. Automated driving has been on the page for quite some time and it's still a very interesting topic. Also, the hype is over and that's good news for us in science, because there were a lot of over-exaggerated expectations and a lot of issues we were facing to get especially public funding for topics which are really necessary to fulfill this vision. But then policymakers believe that in a couple of 2 or 3 or 4 years everything will be fixed and on the market you don't get money. So that's why it's very important that we all understand that we are on a long path towards this automated driving, especially when we should of course only accept it if it is safe and energy efficient. We have seen the first products in the market and I will come to it later, which of course are excellent products and they are safe and energy efficient. That's why they cannot do more than they actually do. And to come to, let's say, use cases where we all as society have benefits from, we need to tackle a lot more challenges. Having this said, I would like to introduce our institute a little bit. We are dealing with several teams here. We are focusing on vehicle concepts with the aim of producing and concepts which really showcase how cars can be long time, let's say some decades, stable in their value, desirable due to upgradability of the major functions and components. We are dealing, of course, with safe and energy efficient automated driving functions. We are dealing with vehicle dynamics and we are using latest technology in computing and sensing. So why are we dealing with automated driving? What's the purpose? We see a lot of potential benefits for customers and society. So individual customers and the society in general. Let me start with the most promising business case from my point of view, which is logistics. And here we see a huge push, especially in the US, due to driver shortage, which will be quite similar in Europe very soon, to keep our logistics and supply chains stable without increasing the prices for our daily goods. We need automated trucks because we don't have enough drivers willing to drive the long distance ways. Also public transport, they are also facing driver shortage. In trams, in buses, all these things are very difficult to staff, and this leads to increase in prices of course. The second one is safety. Maybe this is what you at first bring together with automated driving. Of course, we would like to have safe systems. I would not promise that they are safer than human beings because human beings aren't that bad. There are of course some issues like drunken drivers or very tired drivers. Of course, this is a very bad thing and we can reduce these risks, but we don't need automated driving for that one. I believe that the way towards automated driving will help to increase the public safety due to driving, because we get more and more and even better assistance system, ensuring that we can really help drivers in almost all kinds of difficult emergency situations. The next one, this is a very important one and from my point of view highly underestimated by the public opinion, it's inclusion. Fully automated cars can enable a complete new experience for people with blindness, for instance. Blind people can drive on their own in such a car. And the last one, it's technology. It's all about technology in this field, and it's the most difficult approach where we use artificial intelligence. So imagine we can master these challenges, then we will be in the forefront of applying artificial intelligence to real technical products. And this is much more than presenting some recommendation systems for Netflix or Amazon or I don't know. So this is something which could produce a lot of spillover effects, exactly like the Apollo program in the US. That's why we see this colleague on the moon here. Let me introduce some definitions to you. When we talk about automated driving, we have to talk about the operational design domain, which basically defines under which conditions and where a system can fulfill a given automation level. I will come to the level later. And this ODD refers to conditions, day or night, possible velocities. Is it possible to drive during rainfall or snow and all these things? Where does mean on the highway or on urban roads in a particular country or even in a particular, let's say, facility like an airport or something like that. The SAE level defines the level of autonomy of a system, starting with level 0, which basically means there's absolutely no help, no automation. We have driver assistance, partial automation, which usually is driver assistance in the longitudinal and the lateral direction. Then we have the conditional automation, where you can use the system in automation mode in very tiny particular conditions. Then we have the high automation and the full automation. Basically level 5 is a vision. Nobody believes that we will achieve that anytime soon. And then we should talk about the technology readiness level, which basically comes from the NASA too, but can be derived in all different kinds of industries and applications. We have designed an automated driving readiness level, and you can see a little bit more about that on the IRB 2024 workshop paper by my distinguished colleague Johannes Betz and Melina Ludwitz. This is a usual AD stack, just to make you a little bit more familiar with how we structure the next slides. We have a sense part where we have all the sensors, including the vehicle sensors and the map, where we do the perception task with and without machine learning. We have the fusion, and we come up with a model of the environment. This is handed over to the planner, where we do the route planning, the behavior planning, and lately the trajectory planning. All is based on the model of the environment, including a prediction. Of course, we predict how other road users might behave in the next time step, and are looking for the most likelihood case or the risk minimal case. In these terms, it would be the worst case for us, of course. And the act part, where the controller is controlling all the actuators. So where are we today? The vehicle industry has had its moon landing. It's something, it's not too far-fetched. Everybody in the industry and science is relating to that, and this was really something impressive. Mercedes-Benz has presented their Drive Pilot Level 3 system in a minimal risk use case that's very reasonable, and the ODD is very small. But even it is very small, everybody is referring to this as a moon landing. We have a velocity of maximal 60 kilometers per hour. We need good weather conditions. We are only driving within one lane on a highway, which should be congested because you need to see the next car in front of you. But these cars are privately owned and operated. Mercedes-Benz is selling these cars to end customers in Germany and in selected states of the US. In the meanwhile, BMW is doing pretty much the same. On the other hand side, we have the computer industry's moon landing, which is not better or worse, it's just another case. Here we have a very complex use case, complexer ODD, but as we are in a city, and driving in city traffic, in ordinary city traffic, without some separated lanes or things like that, but only in a very few selected cities, which are quite sunny, and it's operated by an operator, by Waymo in this case, the daughter of the Google company or Alphabet company. So both have very limited operational design domains, but we also see different approaches of different industries with different strategies. So what are the roadblocks? On the one hand side, we have the problem of proving that the system is really safe. I will start with that one. The another one is the energy consumption. Just imagine you have roughly 1 kilowatt for the computation for a level 4 system in your car. What is 1 kilowatt? You can say that with 1 kilowatt hour you could roughly drive 10 kilometers with a very modern and efficient battery electric vehicle. So this is a major concern, of course. So you would lose a lot of your range. But let's start with the safety approval problem. Some figures from statistics. Let's assume that automated driving should be at least as safe as a human driver. Frequently, it is supposed to have a system which is as safe as a well-experienced driver who is in good shape and mood. This is far more difficult. But let's stay with this. Just some figures, 10 years old, but it doesn't change too much. The distance between really fatal accidents, so with people dying, on German highways is roughly 660 million kilometers. Now that's the distance between two fatal accidents on German highways. Let's do a statistical hypothesis test, assuming that the distribution of accidents, as they are rare events, are Poisson distributed. A null hypothesis which says the AD system is not safer than human being. This would be the case that our test which we would like to do was just successful due to luck and not because of the real capability of the system. Choosing a significance level as usual of 5%, which basically is the risk of rejecting the null hypothesis, which in fact is true. The procedure would be, reject this null hypothesis if no fatal accident occurred during 2 billion kilometers of driving on a German highway. Then, if you have mastered this task, then the chance that your system in fact is not safer than the human driver is smaller than this 5%. That's what statistics tell us. Or my colleagues Wachenfeld and Winner. So, how about driving 2 billion kilometers on German highways? No, it's not fun. This is a very expensive task, and you have to do this before you have the safety approval done. So that's not reasonable. You cannot drive 2 billion kilometers with a system you don't know how safe it is. So that's ridiculous from both points of view, from safety point of view as well as from the economic point of view. So the statistic approach alone will not lead to mastering this challenge. The idea is quite simple, and we have seen that for almost 10 years. There were a lot of rumors about Tesla, and the idea is quite easy. Let's integrate such a system in ordinary customer cars. Let the human being stay in charge and drive the car and observe what our automated system, which is in completely so-called shadow mode with no interlinkage or connection to the actuators, so it's risk-free, really risk-free, and look what human being is doing and the system would do if it could, if it was allowed to. Okay, that sounds very good. And we also like the idea very much. So we integrated an AD stack in a tram. Why a tram? The tram is driving in a very reproducible way due to the rail. And of course, we are facing basically all major challenges you face when driving through urban areas. And we found out that for these urban situations, there are so many issues, or let's say deltas, between what the system is doing and what the professional driver actually has done, that you really have to dig into the data with your human brain to find out whether this is a safety critical issue or not. And driving 1 kilometer through Darmstadt here on average brought us several incidents where we have to look at the reference camera systems to find out whether this is a point we have to think about and which is safety relevant or not. So the manual effort is also very, very high when you do silent testing. One could show that on a highway system there is a huge potential to really do shadow mode or silent testing to improve the safety of a system, because there was not so many incidents where manually oversight was necessary to derive a safety argument. A little bit more about this tram system here in Darmstadt. We have been driving this for more than 5 years, collected more than 70 terabytes of data, which of course is a big treasure for us, where we really can analyze what's going on in a city like Darmstadt. It's driving all through the year in normal, regular operation with an ordinary professional tram driver. So, what is it now? We have problems with the statistical approach. Even when we use silent testing, it's not easy and cheap or efficient in any means, even when using silent testing in the city. So what's the way? What we are talking about? We have a desired behavior in our mind, and with our knowledge, we try to bring up a specification, and then we have a specified behavior. And then we implement this and have an implemented behavior. And hopefully all these three, desired, specified and implemented behavior, are congruent. But we can be sure they won't be at the beginning. So what do we need? We need a knowledge-based specification here to come from desired to specified. Then we need a requirement-based verification between specified and implemented. And then for the last one, implemented to desired, there the database validation is the way to go. This is what basically comes from standards like SOTIF, and this slide is basically based on that. The illustration is inspired by the one of TORC. Let me come to the second one, the energy consumption issue. First approach to tackle this would be a relevance-based operating strategy. The state of the art is that all sensors are running at a constant frequency, frame rate, and constant resolution, which usually is as high as it can be. There are some new approaches, like the one of Henning and this year actually, and there the regions around the eco vehicle, so our automated one, are subdivided, and the list of the detected objects is subdivided into relevant and irrelevant, and you don't have to observe the irrelevant one. That's the idea. So only use the relevant parts of the field of view to decrease the amount of data which has to be processed, because the huge amount of data to be processed is causing this huge energy consumption. The definition of relevance is based on the impact on a planned own behavior. So let's assume an object which does not influence the trajectory planning is obviously not relevant. That's the idea. It's inspired by Filion et al. And was further elaborated by Ken Mori and Kai Storms at my institute as well. So, but that's not enough. Let's propagate all uncertainties. Each and every sensor has its measurement uncertainties, which are situation dependent. LiDAR, for instance, can over or underestimate the distance to an object based on the weather conditions. A camera has different ranges, of course, where you can trust depending on fog and rain and all these things, and daylight, of course, or night. So we need all measurement uncertainties. We have to fuse them. Usually we are doing this to decrease the uncertainty, but naturally speaking, we need probability density functions for all the data streams in our process chain here, because only a few of that are deterministic. Most of them are not. So with that, we can enable our planner, for instance, or the fusion approach to really behave like a risk manager. What do I mean by that? We can make all decisions based on the probabilities, and we can demand or ask up and downstream processes to reduce uncertainties, for instance by adjusting the fusion strategy. We need fusion strategies which can be, during the runtime in the customer car, be adapted. So this is something which is basically one of the core elements of a software-defined car, software-defined vehicle, being able to adjust an architecture during runtime, in the runtime environment. So maybe we switch from a redundant approach to a cooperative approach just for a few seconds. We lose redundancy for a couple of seconds, or maybe a split of a second, to be cooperative and find out more about the objects. And then come back to the redundancy. increase the resolution or frequency of signal sensors, or decrease it when it's not necessary and the uncertainties are fine, yeah? To reduce energy consumption. Focus on the sensors on one small region of high relevance and uncertainty. This is possible with the latest FMCW LiDAR systems and telephoto lenses of cameras and all these things to really focus on a field of view. This is basically what we human beings are also doing during driving. Or reduce the velocity of a vehicle, or switch a little bit the angles of orientation to see more what really concerns us. And the other way around is reduce energy whenever the smallest possible uncertainties are not required. A complete other approach, which is more the long-term way, is coming from the computer industry or from the chip technology. Today, all our computers we are talking about here are von Neumann computers. That means that we have a strict separation between the processor and the memory. So basically, data and calculating data are separated. They are interlinked with a bus, and the bus is the bottleneck. Now we have, this is something which comes out, among others, from the Human Brain Project of the European Union, which was a 1 billion flagship project, something called neuromorphic computing, which is much more brain-inspired, human brain-inspired, where we have the neurons and the synapses and the communication in much smaller units here, and we have a lot of these units. So basically we are separating the strict separation of CPU and memory and bringing data and processing of the data together and have it in small portions distributed across a huge area. And this was by Mercedes-Benz illustrating in a use case of artificial intelligence for the sake of energy efficiency in the Mercedes-Benz Vision EQXX, which is known as the most efficient Mercedes-Benz ever. It's a concept car, not a serious car. I was involved in this during my time at Mercedes-Benz, and my team was responsible for integrating a neuromorphic computing approach for the hot word detection of the speech recognition system, just to figure out when "Hey Mercedes" is said. That's the only task of the system. But this is of course something which is running all the time. To be honest, of course, this is not relevant for the range of the car, but it's a nice showcase to show systems which are continuously running, like the ADAS or AD systems, are benefiting from neuromorphic computing. But to go the way down to a safety critical application in ADAS or AD, we have to do much more research, and this is exactly what my institute is doing. On the right hand side here, we see the new way of representing information for being able to use such neuromorphic computing, because they require, at least if you would like to gain the full potential of the energy efficiency, to use spiking neural networks. And these spikes are of course something new, and therefore we need new ways to represent the information. Some of them are using rate coding. You see the different spikes and the number of them and the distribution of them across the time. This is something which is used to represent the information. Others are using the time distance between these spots, temporal coding. And then we have the synapses with the weighting, the postsynaptic neurons, different membrane potentials when spikes are sent, spike responses, and all these things have to be adjusted and tuned to represent the information in the right way. So, having this said, what can we expect from AD in the next 10 to 15 years from my personal opinion? We have seen the Drive Pilot system with a very narrow ODD in 2022. The Waymo Robotaxi, and these are the two cases I started with, came up last year for commercial uses. They have trained and gained experience for at least 3 or 4 years up front at that time here. But that is the commercial case since last year. That's why I only show commercial cases, no safety driver, no temporary test license. These are products. I expect in, let's say, 2 to 3 years, hub-to-hub trucking in the US Sunbelt only. So the big trucks on long distances driving between the huge hubs completely without a human being on board. In this decade, I expect a highway pilot, which is much broader ODD with highway speeds for customer series cars. And next year, hopefully, next decade, sorry, hub-to-hub trucking across the United States, and then of course also in the European Union with the much bigger challenge of different weather situations like the US Sunbelt. And driving only in southern Spain is not a business case. That's why we are not in the pole position here, but our companies are. So Daimler Truck, for instance, or Continental, both are heavily invested and involved in these cases in the US as well. And hopefully, and this would be a huge impact for society, suburban shuttles in Western Europe. What do I mean by that? I really have the concern that automated robotaxis might more or less kill the public transport system we have here in Western European Union. So we need to find a synergy between them. And I believe that line feeding, so bringing people from areas around the major city core to the outer districts where the stations of tram systems and train systems are not so well distributed. This is a potential. So then you can integrate the more rural areas, if you would like to call them rural, to the city cores and the metropolitan areas. And this, of course, is something which would be beneficial for the public transport because higher utilization is always a big concern for them. And it would be a societal benefit because you bring the comfort of a large city in a much broader area around these cities. That would be a nice case, and it's possible because you have dedicated routes. That's something which helps. Which does not help is you should have it in all seasons. It doesn't make sense to only offer such a service during summer or during daylight or things like that. Yeah, for that we need first approval processes. I guess the truck business is front runner here, and we will need new sensor concepts to really tackle the adverse weather conditions. With that, I would like to thank you, and I'm open for any questions. Thanks for your interest.